Okay, so hi everybody and welcome back. What we're going to be doing today is continuing our lecture on conservation of energy, which is covered in chapter 8 of the textbook. So where we left off last time is we introduced the idea of conservation of mechanical energy. We're going to continue on with that, and we're going to look at a bunch of different examples where you can use this idea. So in this example, we have a swinging pendulum. You hold the pendulum with a length of 35 centimeters at an angle of 45 degrees from the vertical. So what you should be envisioning is there's a string, its length is 35 centimeters, it's connected to some sort of mass, and initially the angle the string makes right here with respect to the vertical is 45 degrees. So then you let the pendulum go. Find its speed when it swings down to an angle of 30 degrees from the vertical in meters per second. Okay, so when the pendulum is down here and the angle is 30 degrees from the vertical, we just want to know how fast the pendulum is moving. We're going to assume there's no air resistance, so mechanical energy will be conserved. Let's work this out. Okay, so what we're dealing with is an initial state where the pendulum is released from rest. So that means the initial speed, V initial, is 0. We can also say something about the initial angle. Let's call the angle theta. That's 45 degrees. The final state is where the pendulum has swung down to an angle of 30 degrees from the vertical. So we'll say it swings to theta final is 30 degrees. And what we want to know is V final. The point of the problem is to figure out how fast it's moving. What types of energy do we have to think about? Well, the pendulum certainly will have kinetic energy given by 1/2 mv squared. And it's also going to have gravitational potential energy, which is given by mgy, because the pendulum is moving under the influence of gravity. But the next thing we can say is that since we don't have any non-conservative forces doing work on our system, remember, we don't have air resistance to worry about, that allows us to use the idea that mechanical energy is conserved. Okay, so this just kind of sets the stage. So we can make a table where we have kinetic, we have potential, and we have our initial state and our final. And again, the idea here is just to fill in the table. So initially, there is no kinetic energy because the speed is equal to 0. If we wanted to state what the initial potential energy was, we could just simply say mgy initial. The final kinetic energy would be 1/2 mv final squared, and the final potential energy would be mgy final. Okay, so what we have when we set E initial, the total energy in this initial column, equal to E final, the total energy in the final column, we're simply going to get mgy initial equals 1/2 mv final squared plus mgy final. And notice something that we can immediately do, which is cancel out the mass. So it doesn't matter what the mass of that pendulum ball is, it drops out of the equation. Okay, the next thing we need to do is a little bit of geometry, because in our equation for potential energy, we have y, which represents the height of the pendulum ball, but the information we're given is theta, the angle that the string makes. So let's try to relate those two to each other. So this will be the y-axis, which we use to measure height. Let's say that this is y equals 0 right here, and this is the point of attachment. This is where the string is attached to some fixed point. Okay. The length of the string is L, so that will be L, and then we have our pendulum mass over here. And then this would be the angle theta that the pendulum makes with the vertical. Okay, so what we're trying to find out is what is a way of describing y, the height of that pendulum mass? Well, the length L can be considered the hypotenuse of a right triangle, and this vertical side is the adjacent side. Okay, because what we have here is a right triangle, we can identify L as the hypotenuse, and this side, this vertical side, as the adjacent. And since cosine of theta is equal to adjacent over hypotenuse, or adjacent divided by L, the adjacent side we want is just L cos theta. But we're going to put a negative sign on that because it's below 0. Okay, so in other words, if y equals 0 is up here, this is somewhere below that, so it has a negative y value. Okay, so now here's what we're going to do. We're going to take the equation we wrote down, where we set the two energies, initial and final, equal to each other, and we're going to replace, every time we see y, we're going to replace that with minus L cosine theta. So on the left side, we have g times y initial. That's going to become g times minus L cosine theta initial. Then we have a half v final squared plus g. Y final is going to be minus L cosine theta final. Okay, so we're just replacing y with minus L cosine theta. Okay, so now we solve for v final. We have a half times v final squared. If I want to isolate that on one side, I'm going to have minus GL cosine theta initial. But if I add this term to both sides, I'm going to have plus GL cosine theta final. And then if I multiply by 2 on both sides, I'll get that v final squared is equal to 2. We have a factor of g and L in both of those terms, so we'll pull that out. And then I have cosine theta final minus cosine theta initial. And of course, I just need to take the square root of that to get the speed. So I'm going to have 2 times 9.8 meters per second squared. L, that's the length of the string, is 0.35 meters. And then I have cosine theta final, which is 30 degrees, minus cosine theta initial, which is 45 degrees. So if you do this calculation, it's going to come out to 1.044 meters per second, but we'll round that to 1.04 meters per second. So we were able to use conservation of mechanical energy to figure out the final speed of the swinging pendulum. Next thing I'd like to go through is a really famous physics demo, which is commonly done in introductory physics courses when students are learning about energy for the first time. And I wish we were able to do this in person this year and you were able to try it out yourself. But we'll do the next best thing and look at a video of this experiment. And it's going to be performed by Neil deGrasse Tyson over here. And the basic idea is this. You have a chain hanging from the ceiling. So there's the chain. And it's connected to a bowling ball. So what Neil deGrasse Tyson is going to do is start with the bowling ball touching his nose. And then he's going to release the bowling ball from rest. So it's going to swing to the other side of the room, then it's going to swing back, and he's going to make sure that he's standing perfectly still throughout this experiment. Oops. So here it goes. Okay, so if you try this out on your own, it's a little bit scary because there's a huge bowling ball swinging towards your face, but you can actually be perfectly confident that the ball is not going to hit you in the nose if you do this, okay? So why is that? Try to think of why Neil deGrasse Tyson can be so confident that the ball's not going to hit him in the nose? And also, as a follow-up, would he be safe if he gave the ball a little push instead of just releasing it from rest? So think this over for a few seconds, pause the video, and see what you come up with. Okay, so to understand how the demo works, we're going to draw a little picture. We have the person, this is their head, and this is the bowling ball that starts off initially just touching their nose. So the initial speed of the bowling ball is 0 because it's released from rest. And we can indicate the initial height off the ground of the bowling ball as y initial. Okay, so what happens next is that the bowling ball is released, so it swings down like this and then back up on the other side. Then it swings back the other way, back towards your face. Okay? So if we imagine that on the swing back towards your face, it hits you in the face really hard, what that means is if your face were not there, it would overshoot. So it would end up over here, let's say, if your face were not there. Okay, so let's put this as y final. Final height. Okay, so now let's bring in the idea of mechanical energy. So the total mechanical energy of this bowling ball is K plus U. So kinetic plus potential. And if we want to find out the initial energy, well, that would be 0 kinetic plus mg y initial for the potential. But if we imagine that this is the final state, then the final energy is going to be 0 kinetic because it has to come to a stop at the highest point, plus mg y final. But if y final is bigger than y initial, that would imply that E final is bigger than E initial. So somehow the ball has more energy at the end than what it started with. That's just not possible. Where did that energy come from? Energy has to be conserved. So in particular, if we have no air resistance, okay, this means y initial is equal to y final. So it swings back to the same exact height that it started from because, of course, when we have no air resistance, initial and final energies are the same, so that implies initial and final height would also be the same. So that's describing a situation where the ball swings to the other side of the room, swings back, and then it just barely grazes your nose when it swings back. Okay, it doesn't hit you in the face. If we do have air resistance, by the way, then if we do have air resistance, then y final is going to be a little bit less than y initial. So it's not even going to come exactly back to the height it started from. It's going to fall a little bit short of that, maybe something like this. Okay, because it's going to lose a little bit of energy because of that air resistance. Now, on the other hand, if we give the ball a little push, then it's no longer true that we start with no initial speed, okay? So the ball has a little bit extra energy, okay? And in that case, it can swing back and hit you in the face if you give it a little push. So in this experiment, one really important thing to do is to, of course, stand still so that you're not leaning into the swing of the ball, and also to not give the ball an initial push because then it will actually come back and hit you in the face. Okay, so in this example, we have a block with a mass of 2.5 kilograms, which is dropped from a height of 1.5 meters onto a spring, which has a force constant of 474 newtons per meter. So what you want to imagine is the block is dropped and it falls straight down. It touches the spring, but it doesn't come to a stop right away. Instead, what happens is it compresses the spring, And as it compresses the spring more and more, it slows down more and more. And at some point, it's going to come to a stop. Okay, so what we want to know is, at the moment it comes to a stop, how much is the spring being compressed from this initial equilibrium length? So as we do the problem, we're going to assume that mechanical energy is conserved. And that just means there's no air resistance as the block moves down. There's no friction, no non-conservative force of any kind doing work on the system. Okay, so let's start by drawing a picture of the system. The initial state looks like this. We have a block, and it's above the spring. And what we'll do is we'll draw a y-axis to keep track of where the block is at any given moment in time. So this will be y initial, where we start. And also just remember that we're free to set the 0 point for our y-axis anywhere we like. So I'm going to put it right here. In other words, I'm going to say y equals 0 is just the position of the spring starting off. So that tells us immediately that y initial is 1.5 meters, because we're 1.5 meters above the 0 point. Also, v initial is equal to 0 because we released the block from rest. So it doesn't have any initial speed. Okay, next we'll draw the final state of the system, where we have a block now on top of the spring, and the spring has been compressed by some amount. Okay, so let's indicate where the block ends up in the final state. Let's show that position on the y-axis. We'll call that y final. And notice a couple of things. First, we don't know what y final is. That's our job to solve for it. And we do know that v final is equal to 0 because the block is brought to a stop. Okay, so it's not moving in the final state. Okay, so as far as y final is concerned, we should look at the picture and realize that that's what we're trying to solve for. Okay, y final tells you how much the spring has been compressed. So first, let's note that y final is going to be something negative. And that's because it's below 0. It's below the 0 point. So let's say y final comes out to negative 10 centimeters. Well, that would just mean the spring has been compressed by 10 centimeters. If y final came out to negative 20 centimeters, then we're compressed by 20 centimeters. So the goal here is to find y final. That will tell us how much the spring has been compressed. Okay, so what types of energy do we have to deal with? Well, we have kinetic energy, 1/2 mv squared, because we have a block that's moving. We have gravitational potential. That would be given by mgy, because the block is changing in height and it's falling under the influence of gravity. But we also have spring potential energy to worry about now. And remember, this is given by 1/2 kx squared. So these are the three forms of energy to consider in the system. We know that there aren't any non-conservative forces doing work, so WNC is 0. That's why we can use conservation of mechanical energy. So mechanical energy is conserved. Okay? So there are different ways we can say mechanical energy is conserved. One of those ways is to say that delta K plus delta U gravitational plus delta U for the spring is equal to 0, okay? So if I look at delta K, what's my final kinetic energy? Well, it's 0 because the block has been brought to a stop. What's my initial kinetic energy? It's also 0 because the block starts from rest. If I look at delta UG for gravitational, well, my final value is mg y final. And my initial value is mg y initial. Okay? What about the spring potential energy? Well, my final value is 1/2 times k times the amount of compression squared. But again, we said earlier that the amount of compression is just y final, so we'll square that. And then initially, the spring is not even compressed at all, so we have 0 initial potential energy for the spring. And when we add all that together, we get 0. By the way, we could have done this by drawing a table and looking at all the energy in the initial column and in the final column and setting those equal. That would give you the same exact equation. So all I'm doing here is showing you a different way you can think about conservation of mechanical energy. Okay? Okay then, so what we'll do next is simply plug in the known values. Okay? So I have 1/2 here. I'm gonna do this down here. I have 1/2 times K, which is 474. Units are newtons per meter, but we can also write that as a kilogram per second squared. And then we have Y final squared. Okay, so I took care of this term. Next, let's do this term, mg Y final. So I have plus, the mass is 2.5 kilograms. G is 9.8 meters per second squared. And then Y final. And then I have minus mg times Y initial. That's the last term to think about. Okay, so I have the mass once again. That's 2.5 kilograms. G is 9.8 meters per second squared. And then Y initial is 1.5 meters. And that all equals 0. So what I did is I took our symbolic formula and plugged in the known values. Okay, so the first term is 1/2 times 474. That's 237. We have Y final squared, multiplying that. The second term is 2.5 times 9.8. That comes out to 24.5. And we'll have a unit of meters going along with that. So let me just explain what I'm doing with the units here. I want to multiply on both sides by seconds squared over kilograms. So we'll cancel out all the units in the first term. And we'll be left with only units of meters in the second term. And in the third term, I have to multiply that by Y final. Don't forget that. And in the third term, I have 2.5 times 9.8 times 1.5, which is negative 36.75. Again, if I multiply by seconds squared, I cancel out seconds squared on the bottom. If I have kilograms on the bottom over here, cancels with kilograms over here. And then all I'll be left with is meters squared. And of course, if I do the same thing on the other side, I'm just multiplying by 0, so nothing changes. I still have 0 on this side. Okay, so this is a quadratic expression where the A term is 237, the B term is 24.5 meters, and the C term is minus 36.75. Oops, that should be a 5. Meters squared. Okay, so how do we solve for Y final? We use the quadratic formula. So it's minus B plus or minus the square root of B squared minus 4AC divided by 2A. Okay, so basically just plug in the values of A, B, and C that we found here, and you're always going to get two possible solutions when you use the quadratic formula. So the first one is plus 3.3454 meters. The other one is negative 0.4488 meters, and we'll keep 3 sig figs on the answer. So the question now is, which one of these am I going to pick? Well, at the very beginning we said that y final is going to be negative because we know the block ends up below the 0 point, okay? So we're going to pick the negative solution. That must be the correct one. So we choose the negative root. Which rounds to about 0.449 or negative 0.449 meters. In centimeters, we could say 44.9 centimeters of compression. Okay, so that would be the answer. Okay, so we'll do another example. And in this case, we're dealing with a cart that goes into a loop-the-loop in an amusement park ride. So we have an 1,800 kilogram cart, which is set into motion by compressing a spring that has a force constant K of 1.5 times 10 to the 5 newtons per meter. Okay, so the initial state looks like this. We have the cart up against the spring, which is compressed by some distance, and we know the spring is storing some energy when we do that. So we release the cart, then it shoots off this way. It goes into the loop-the-loop, which has a radius of 12 meters. We're going to assume that throughout the motion, mechanical energy is conserved. So of course, that means there's no friction and there's no air resistance acting on the cart as it moves. The question for us is, what is the minimum distance x right here? The spring has to be compressed in order for the cart to actually make it through the loop. So the idea is this. We can imagine if we don't compress the spring that much, so x is something small, when we shoot the cart off, it's moving pretty slowly, so it doesn't actually make it around the loop, right? It might stop short up here somewhere. On the other hand, if x is really big, so we compress the spring a lot, the cart is going to be moving very, very fast as it shoots out of the spring, and it will easily make it around the loop, no problem. So there's some minimum distance we need to compress the spring such that the cart will actually make it around the loop. That's what we're trying to find. What is the minimum amount of compression over here such that the cart actually makes it around the loop? So there's a little bit of a hint here, okay? The hint is that the cart must be in contact with the track at all times. We don't want it to fall out of the track, right? That would be bad. So the normal force, in other words, between the cart and the track has to be greater than 0. If the normal force is going to 0, that means the cart is falling out of the track. That's bad. That's not what we want. Okay? So let's work this one out. Okay, so we'll start just by writing down the situation. The initial state of the system looks like this. The spring is compressed fully, and the cart is at rest. So the cart hasn't begun to move yet. So in the final state, remember, we want the cart to be able to make it all the way around the loop. So that means it has to make it to the highest point. So the cart is at the top of the loop. But now the spring is relaxed. There's no cart pushing against the spring, so it's just in its equilibrium position. What types of energy are we dealing with here? So we have kinetic, of course, because the cart is moving, 1/2 mv squared. We have gravitational potential, mgy, because gravity is a force we have to consider. And then also we have a spring potential energy, which is 1/2 kx squared. Okay? So we're assuming mechanical energy is conserved. So when we make the table, we have kinetic, we have spring potential, we have gravitational potential. We can look at the initial state and the final state. And let's start with kinetic. So in the initial state, The cart doesn't have any kinetic energy, so we can put that to 0. It's not moving. And in the final state, it might be moving at some speed, which we call v final. So let's just put that as 1/2 mv final squared. When we consider the spring, in the initial state, well, it's compressed by a distance x, so we have 1/2 kx squared. But in the final state, it's perfectly relaxed, so 0 would be the final potential energy. Okay, when we think about the gravitational potential energy, it helps to draw a picture. So here's the loop. And let's say that this is our y-axis, which we use to think about heights. Okay, let's set y equals 0 down here on the ground. So actually our initial gravitational potential energy, because y is equal to 0 initially, y initial is equal to 0. That would be 0 as well. But then our final height is up here. How do I know what that height is? Well, it's just the diameter of the loop. Okay, so that would be 2 times the radius of the loop. So the final height is 2r. So I'd write this as mg times 2r. Okay, so since mechanical energy is conserved, E initial is equal to E final, which means I take the initial column and I add up all the energies. But the only thing that's there is 1/2 kx squared. And in the final column, I do the same thing, where I have 1/2 mv final squared plus 2 mgr. And what I'm trying to do here is solve for x, right? I want to know how much the spring is initially compressed. But I'm not quite ready to solve for it because I don't know what v final squared is. So what is the speed of the cart when it's at the top of the loop? So we'll do kind of a little bit of side work to say, what is v final? So to answer the question, we'll look at a free body diagram of the cart. At the top of the loop. Okay, so this is what it looks like. We have the circular loop. There's the cart. Now, what forces are acting on it? Well, we have the force of gravity, or the weight, that points straight down. And we should also have a normal force because there's contact between the cart and the track. Now, the normal force is going to be pointing downwards because the cart is upside down. So remember, the normal force pushes away from the surface, which is going to be downwards in this case. Okay? So then what we'll do is we'll apply Newton's second law. The net force in the radial direction is going to be m times ar, acceleration in the radial direction. This is what we typically use when we're dealing with circular motion, okay? Okay, so the two forces that are acting in the radial direction are the normal force and the weight. The normal force is pointing inwards towards the center of the circle, so that's positive. And so is the weight. That would also be considered positive because it's pointing towards the center of the circle. So when we add the two forces in the radial direction, we just have n plus w. And that equals m times the acceleration, which is v squared over r. That's how we do the acceleration for something that's moving in a circle. Okay, so the next thing we'll do is we'll say if n goes to 0, that means the cart is just about to fall out of the track. Because, of course, n going to 0 means there's a loss of contact between the cart and the track. Okay, so if that's the case, then we put 0 for the normal force. We put m times g for the weight. And that equals m times v squared divided by r. cancel out the mass. What do we get? V squared is equal to G times R, okay? This is telling us the minimum speed the cart needs to have at the top of the track so that it doesn't fall out. If it moves any slower than that, it's going to start falling out of the loop, okay? So that's the speed that we're going to want to use in our energy equation. So we have 1/2 kx squared equals 1/2 times m. And then v squared is g times r. That's what we just found. And then we have plus 2m gr. Okay, so we have 1/2 kx squared. We have 1/2 plus 2 multiplying mgr. So 1/2 plus 2 is 5/2. And you can cancel out a factor of 2 on each side. And then you can divide through by k. So x squared is now going to be 5 mgr divided by k. And of course, we'll square root that to get x. So x will be the square root of 5 times the mass, which is 1,800 kilograms, times g, which is 9.8 meters per second squared, times r, which is the radius of the loop, which is 12 meters. And we'll divide that by k, the spring constant, which is 1.5 10 to the 5 newtons per meter, but we can also write this as kilograms per second squared. And when we do that, let's see how the units work out. Kilograms cancel, seconds squared cancel. And then we just have meters squared inside of the square root, but that gives us meters after we square root it. And this works out to 2.65 meters. But if we're keeping track of the sig figs, we'd want to keep just 2. So we'd round that to 2.7 meters. So in other words, you have to compress the spring by at least 2.7 meters in order for the cart to make it all the way around the loop. Anything more than that, it works just fine. You'll still make it around the loop, but anything less than that is not going to work. All right, so next we're going to move on to conservation of energy. So what we talked about previously was conservation of mechanical energy, which only applies in certain special cases. So you can only use this concept when you have no friction and no air resistance, basically. So now we want to develop sort of a more general version of that applies in every case, not just when we have no friction and no air resistance. Okay, so we'll start by doing a simple calculation. And the scenario is this. We have a Chicago Cubs fan standing on top of the Sears Tower, which, by the way, has a height of 443 meters above street level. So this fan is going to drop a baseball, which has a mass of 143 grams, from the top of the tower, and it's going to fall to the ground. Okay? So we know that realistically there's going to be some air resistance acting on the ball as it falls. And because of that, it's not just going to accelerate and move faster and faster forever. At some point, it's going to reach what we call a terminal speed. And after it reaches that terminal speed, it doesn't speed up anymore. It just continues down at that terminal speed until it hits the ground. So let's say the terminal speed for this baseball is 42 meters per second. What I want you to do is find the amount of mechanical energy that's lost because of air resistance as the ball falls to the ground. So remember, mechanical energy is kinetic plus potential. What I'm asking you to do here is calculate the change in mechanical energy from this starting state to this ending state where the ball is just about to hit the ground. So pause the video, see if you can work it out, and then we'll go through it together. Okay, so what we're calculating here is a change in mechanical energy. So in other words, E is K plus U. So delta E, the change in energy, change in mechanical energy, I should say, is delta K plus delta U. All right, so how do we write delta K? Well, that's going to be 1/2 mv final squared minus 1/2 mv initial squared. Delta U, that's going to be mg y final minus mg y initial. Okay, well, we can cancel out a few things here because V initial is equal to 0. The ball starts from rest. So the initial kinetic energy is going to be 0. Also, we can cross this one off because the ball ends up at street level. And that's where we're going to set y is equal to 0. Okay? All right, so we have delta E is equal to 1/2 mv final squared minus mg y initial. The way you can think about this is that in the final state, all of the energy is kinetic. It has no potential energy, it's all kinetic. And in the initial state, it doesn't have any kinetic energy, it's all potential. So the difference between those two gives you the overall change in mechanical energy. So now we can just plug the numbers in. The mass of the baseball is 143 grams, which would be 0.143 kilograms. That final speed is 42 meters per second. So we'll square that. Then we'll subtract m 0.143 kilograms times g, 9.8 meters per second squared. And then y initial is the height that the ball starts off at, which is 443 meters. Okay, so if you do this calculation, you're going to get something negative. It comes out to about 494.69, but we keep 3 sig figs on that. Unit-wise, we have kilograms, we have meters squared divided by seconds squared, which you should remember is equivalent to a joule. So the negative sign means the ball is losing mechanical energy. So it has less at the end of the process than what it started off with. That's what the negative sign means. So we would say 495 joules of mechanical energy are lost. And basically what we're demonstrating here is when you do have a non-conservative force like air resistance, the effect of it is to change the mechanical energy, okay? So without air resistance, there would be no change in mechanical energy, but with the air resistance, we're actually losing mechanical energy. That's the idea. Okay, so now we're at a point where we can relate the mechanical energy of some system to the non-conservative forces like friction and air resistance that may be acting on it. So remember, mechanical energy is defined as E equals K plus U. So mechanical energy is the sum of kinetic and potential energies. And what we just saw in the previous example is it's not always conserved. It's possible to lose mechanical energy. That happens when you have non-conservative forces doing work on a system, okay? So the way we write this in equation form is that the work done by non-conservative forces is equal to delta E. That equals the change in mechanical energy. So since mechanical energy consists of kinetic and potential, we can also write this as work done by non-conservative forces equals delta K plus delta U. Okay, that's what the equation says. The total work done by all the non-conservative forces acting on your system is the total change in mechanical energy of the system, which again is delta K plus delta U. That's how you interpret this. So in the previous example we looked at, air resistance is doing negative work. So W, the work done by non-conservative forces, is something less than 0. It's something negative. And therefore, delta E, the change in mechanical energy of the ball, was also less than 0. It was something negative. So that's how you apply this new idea to the previous example. But what we should do next is prove this result. Where does this actually come from, and how can we understand where it comes from? Okay, so this is a bit of a derivation, and what I want to start with is the work-energy theorem. So back in chapter 7, we learned that W net is equal to delta K. And what this says is if you take the total work done by all the different forces acting on an object, that equals the change in kinetic energy of that object. So what we'll do with that is we'll break W net into two pieces. We can have work done by conservative forces and also non-conservative forces. Okay? So in other words, W net will be WC for conservative plus WNC for non-conservative, and that will equal delta K. Okay, the next thing we can notice is that anytime we have a conservative force, we can define a potential energy. So in other words, for any conservative force, we have a potential energy. And do you remember how to relate the two? It's given by, here, the change in potential energy is equal to minus W. That's how we define it. So therefore, when I see the work done by the conservative force, I can replace that with minus delta U. And then we'll add that to WNC. That equals delta K. So just shift the minus delta U over to the other side, and we'll have WNC equals delta K plus delta U. That's what I wanted to prove to you guys. So that the work done by non-conservative forces is just the change in kinetic plus the change in potential, which is just the overall change in mechanical energy. But notice what happens if WNC is equal to 0. So if we're dealing with a situation where there are no non-conservative forces doing work, then what we have is delta K plus delta U is equal to 0, which is just a statement that mechanical energy is conserved in that case. Okay? So the point is, in general, mechanical energy won't be conserved because you could have things like friction or air resistance changing the mechanical energy. But if those things are not part of your system, if we don't have non-conservative forces doing work, then mechanical energy is conserved. Okay? Okay, so let's do an example now where we can put this new result that we derived to use. And if you look at this problem, it should look familiar. I assigned this one on the first week of class. And the way you probably solved it on the homework assignment was to use Newton's laws of motion. So in addition to being a good example of how we can use this new result, this is also an example of a problem that can be solved in many different ways. So if you solve this using Newton's laws, you'll get the same answer as if you use this new energy method. Okay? So here's what's going on. A penguin slides down an icy incline. The coefficient of kinetic friction between the incline and the penguin's stomach is 0.15. So there's going to be friction as the penguin slides down. The angle of the incline is 25 meters, and the distance down the incline is 25 meters. The penguin gets a running start so that his speed is 2.5 meters per second when he begins to slide down the incline. What is the penguin's speed when he reaches the bottom of the incline? Okay, so let's work this out. Okay, so we'll start by just writing down what the initial state is. So the initial state is the penguin is at the top of the incline. And the final state is the penguin is at the bottom. So that's pretty simple. Now, the initial speed when the penguin is at the top is 2.5 meters per second. The final speed when the penguin is at the bottom is not something we know, and it's something we need to solve for. Okay, so what types of energy are we dealing with? Well, the penguin has kinetic energy, so that's going to be given by 1/2 mv squared. And there will also be gravitational potential energy because gravity will be acting on the penguin as the penguin slides down the incline. But we also now need to think about non-conservative forces that are doing work. Non-conservative forces doing work, that would be kinetic friction. Okay, so our equation, therefore, is the work done by non-conservative forces, which is friction. So work done by friction is equal to delta K plus delta U, but specifically we're talking about gravitational potential energy. Okay, so what we're going to do next is just come up with a formula for each one of these three terms in the equation. So how about we start with kinetic energy, delta K? Well, that's going to be given by 1/2 mv final squared, which is what we want to find out, minus 1/2 mv initial squared. So that's pretty straightforward. What about delta U? Well, that's going to be mg y final minus mg y initial. So let's do a little bit more work to see how we can write that expression out. Remember, the penguin is on an incline. The distance down the incline is d, and the angle of the incline, let's call that theta. So I'm going to draw a y-axis so we can keep track of the height of the penguin. Penguin starts off at this initial height and ends up down here at this final height. The most convenient thing to do is just to set that final height to 0. So in other words, we'll put the 0 point at the bottom of the incline. And then we can ask the question, what's y initial in that case? Well, it's just a little bit of trigonometry. We have a right triangle here. And basically this side length is y initial. So if we use the definition of the sine function, remember sine is opposite over hypotenuse. In this case, the opposite side is y initial. The hypotenuse is d. And what that tells us is y initial is d sine theta. And again, y final is 0. So what we have for the change in potential energy is 0, because y final we plug in is 0, minus mg times d sine theta. Okay. All right, so the last thing we need to do is figure out the work done by the friction force. But in order to do that, we actually need to figure out what the friction force actually is. So remember, friction kinetic is given by mu k times n. We need to know the normal force in order to know the friction force. So if we draw a little free body diagram of the penguin, so here, free body diagram, FBD of penguin. Put a little dot representing the penguin. And again, the idea is we're going to draw all the forces. So we have gravity, Fg, going straight down. We have friction going up the ramp, opposing the motion. And then finally, we have a normal force pointing perpendicular to the surface of the ramp. I'm going to draw a coordinate system that we'll use. X is going straight down the ramp, Y is going out of the ramp like this. And so in that coordinate system, I can break the force of gravity into components. So this would be FGX, the part that's going down the ramp. And the part that's going into the surface of the ramp is FGY. That would be a right angle, because X and Y are always at right angles. And this would be the angle theta of our ramp. Okay, so in this right triangle that I drew, let's think about cosine theta. Cosine of theta is defined as the adjacent side over the hypotenuse. So FGY divided by FG. So therefore FGY, because we're going to need to know this later, is equal to the force of gravity times cosine of theta, or just mg, because that's the force of gravity, times cosine of theta. So the reason I did all that is now I can use Newton's second law. The net force is equal to mass times acceleration, and we can specifically look at the y direction. Because if we do that, we can solve for the normal force. Okay, what forces do I have going in the y direction? Well, I have the normal force, which is positive, and I have FGY, which is negative. It's going in the negative y direction. And that equals the mass of the penguin times the acceleration in the y direction. But here's the thing. There is no motion in the y direction, as we've shown it in this diagram here. So, therefore, we can set the acceleration of the penguin equal to 0. So just to be clear about what I'm saying here. So the penguin is not moving this way, not moving out of the ramp or into the ramp. The penguin is only moving this way, down the ramp. That's why we can set AY equal to 0. So I'll have N minus FGY, which is mg cos theta, as we just said. That equals 0. So therefore, N is equal to mg cos theta, and then therefore, the friction force is equal to mu k cos theta. Okay. So now what we want to do is find the work done by that force. So the way we calculate work, if we have a constant force, is just take the force itself, which is Fk, times the distance, which is how far you slide down the ramp, times cosine of an angle we call phi. And remember, phi is the angle between your force and your displacement. Okay? So what we have is a displacement going down the ramp in the positive x direction, and we have a force going up the ramp in the negative x direction. So what's the angle between those? They're pointing in opposite directions. It's 180. Okay, so for friction, that's always how it's going to work. The angle between force and displacement is going to be 180. Our force is mu k mg cos theta. Distance, just leave it as d, and then we have cosine of 180. Cosine of 180 just brings out a negative sign. So we have mu k mg times d times cosine of theta. That's the work done by friction. Okay, so now we're going to put all of that together into one single equation. Remember, here I'm going to actually put a little box around the equation we're using. This says the work done by friction is delta K plus delta U. So the work done by friction is minus mu K mgd cos theta. Delta K is 1/2 mv final squared minus 1/2 mv initial squared. And then delta U is minus mgd sine theta. So here, let's put a little check mark by each one of those. There's delta K, plug that in here. There's delta U, and there's the work done by friction. Okay, so that's what we're plugging into our energy equation. So notice that one thing we can do is immediately cancel out the mass, just divide it out on both sides. And again, we're trying to find V final. So if I solve for V final here, let's say 1/2 V final squared is equal to 1/2 V initial squared. So I put the V initial term on the other side, plus GD sine theta, and then minus mu k g d cosine theta. Okay, so V final squared, just multiply through by 2. I'm going to have V initial squared. And then I'll have plus 2 for both of these last two terms. I have a common factor of g and d, so I'll just pull that out. And then I'll have sine theta minus mu k cos theta. Okay, so all I need to do now is plug in the numbers. V final is the square root. Okay, V initial squared is 2.5 meters per second, square that. Then I'm going to have plus 2 times g, 9.8 meters per second squared, and then d is the distance down the ramp. That's going to be 25 meters. And then I'm going to have sine of the angle of the ramp, which is 25 degrees, minus mu k, which is 0.15, times cosine of the same angle. That's the calculation we need to make. Comes out to about 12.1, but we'll keep 2 sig figs. So about 12 meters per second when the penguin reaches the bottom of the ramp. Okay, so let's do another example where we get to use our result that we derived. And in this case, we're going to do a very similar problem to what we did earlier, where we have a block being dropped onto a spring, but we're going to add a little complication. We're going to say that there's also friction while the block is falling down. Okay, so a block of mass 2.5 kilograms is dropped from a height of 1.5 meters onto a spring with a force constant of 474 newtons per meter. So now as the block is falling, I want us to imagine there's a constant friction force of 22.5 newtons that's acting on the block. So where is this friction coming from? Well, you might imagine the block is sandwiched in between two walls and there's friction exerted by those walls as it falls down. We won't have to calculate the force of friction. We're just going to use the given value, which is 22.5 newtons. Okay, so we know what happens. The block falls, it hits the spring, and then it doesn't just come to a stop immediately. The spring gets compressed, and then eventually it brings the block to a stop, but only after being compressed by some amount. So the question we're answering is, at the moment the block comes to a stop, how much is the spring compressed? Okay, so we'll assume there's no air resistance, just that friction force. Let's see what we get. Okay, so let's first say that in the initial state, the block is released from rest. And that means V initial is equal to 0. In the final state, we have the block brought to a stop by the spring. Which means the final speed will also be 0. Okay, let's think about what types of energy we're dealing with. So we have kinetic. Because we have a block falling down, it has some kinetic energy, 1/2 mv squared. We have gravitational potential, mgy. We also have spring potential energy, 1/2 kx squared. What about non-conservative forces? Well, just like in the previous problem, the non-conservative force doing work on the system is friction, kinetic friction. Okay, so therefore, the energy equation we're going to be using is the work done by friction
equals delta K. And then we have two delta U terms with two types of potential energy. So we'll have delta U G plus delta U S. That's how we'll write it. And to draw a picture of the motion so we can make sure we are getting the heights correct, let's draw a y-axis. We have the block in the initial state, some distance above the spring. Let's put the 0 point for the y-axis at the position of the spring initially, which means the initial height of the block, y initial, would be 1.5 meters. Okay, what does the final state look like? The block is on top of the spring and the spring is compressed. We want to know how much it's compressed by, so we should figure out what y final is. We don't know what y final is, but we'll solve for it in this problem. Okay, so now we have four different terms in our energy equation. Our job is going to be to figure out an expression for each one. Let's start with kinetic energy, delta K. Well, here's the thing. If we start off at rest and we end up at rest, the kinetic energy is 0 in both cases. So we basically just have 0 minus 0. Final minus initial is just 0 minus 0, which is no overall change, right? If you start at rest and you end up at rest, there's no overall change. For gravitational, we're going to have mg y final minus mg y initial. Okay. For the spring is not initially compressed, so we're going to have some final energy, but the minus initial will be just minus 0. And in the final state, we're compressed by an amount equal to y final. So I'll just write this as 1/2 k y final squared. Again, we subtract 0, indicating there is no potential energy in the spring initially. Okay. What about the work? The work done by friction. Okay, so the way we calculate work, again, is we take the force, which is friction, times the distance, times cosine of the angle between the force and the displacement. So let's start with the distance d. This is the total distance the block moves on its way down. That's right here. Well, the way we could think about that distance, it's basically y initial minus y final. So if we take this value of y initial up here and we subtract this value down here, we simply get the distance the block has moved. Okay? What about the angle? Well, as the block is falling, you want to think about the friction force is going up and the motion is going down. The angle between those two is 180. So what we have is Fk times y initial minus y final times cosine 180, but cosine 180 is just a negative sign overall out front. So we have minus Fk, y initial minus y final. That's how we write the force, the work done by the friction force. Okay, so let's take the energy equation. We have all the different parts of it now. On the left side, we have the work done by friction, so that's going to be minus Fk, y initial minus y final. That's going to equal delta K, which is 0, plus delta U for gravity, which is mg y final minus mg y initial. And then delta U for the spring is 1/2 k times y final squared. So we're just taking the energy equation and plugging in all the different expressions that we worked out. Now at this point, the rest is just algebra. The only unknown variable in this equation is y final, so we want to find it. But we'll clean the equation up a little bit, okay? So the first thing we'll note is that I want to set the left side equal to 0. Okay, so I want to move everything over to the right side of the equation, so the left side will just be 0. And the first term is 1/2 k y final squared. So we only have one term in the equation with a y final squared in front of it. That's the one. Now we have two terms with just y final to the first power in it. So we have this one, and then we have this one. And we want to combine them into one term just to make it a little easier. Okay, so I have m times g multiplying y final. On the other side, I have the force of kinetic friction multiplying y final. But if I subtract that over to the other side, I'm going to have minus Fk, and that multiplies y final. Okay? Next, we'll notice we have two terms with y initial in it, this one here, and this one over here. We want to combine those into one, just to make it a little simpler. Okay, so on the left side, I have minus Fk times y initial. But if I add it to the other side, I'll have positive Fk on the right side, and then minus mg times y initial from the second term. All right, that's my formula. And it kind of looks like we're going to have a quadratic formula at the end of the day. Let's plug in everything we know. So we have 0 equals 1/2. K is equal to 474. Newtons per meter, or we can say kilograms per second squared. Multiply that by y final squared. Then the second term is, I have the mass, which is 2.5 kilograms, times g, which is 9.8 meters per second squared. And then minus the force of friction, which we're given, is 22.5 newtons. But I'm going to write that as a kilogram times a meter per second squared. That's equivalent to a newton. And then that multiplies y final. Okay, then the last term is plus, we have that same force of friction, 22.5. Again, I can write newton as a kilogram times a meter per second squared. And then I subtract m times g, which is 2.5 kilograms, times 9.8 meters per second squared. And then y initial, which is coming right here, is 1.5 meters. Okay? So here, let me put this in brackets so it's a little bit more clear. I'm taking the whole thing in brackets times 1.5 meters. Okay, so that is definitely a quadratic expression. If you take a half times 474, you get 237 times y final squared. If you calculate this whole thing, 2.5 times 9.8 times minus 22.5, that actually just works out to 2. And that just multiplies y final. And then if you calculate this whole thing here, you're going to get minus 3. By the way, units, how do they work out? Well, how about on both sides of the equation? We multiply by seconds squared divided by kilograms. So if you do that on the left side, you're just multiplying by 0, so you still get 0. If we look at this term, you'll cancel out all the units. If you look at the second term, you'll just be left with meters, which is why I wrote it as meters. And if you look at the last term, you'll be left with meters squared. Okay, so this is a quadratic expression where the A term is 237, the B term is 2 meters, and the C term is minus 3 meters. So how do we solve this to get y final? We just use the quadratic formula, which is minus b plus or minus square root b squared minus 4ac over 2 times a. And again, I'm not going to show the calculation because basically just punch the numbers a, b, and c into your calculator. And we'll get to 2 possible solutions. One of them is positive, 0.1083 meters. The other one is negative, 0.1168 meters. Again, we have to decide between the two. But notice how y final has to be something negative because we're below 0 at the end of the day. So we'll choose the negative solution. Which is minus 0.117 meters when we round it to 3 sig figs. So we can say the spring is compressed. Spring is compressed 11.7 centimeters when the block comes to a stop. So that's the answer. Okay, so we'll end this video here. I'll see you in the next one. And until then, take care.